All right, so as promised, guys.
Okay.
So what we are going to do today is to introduce to you sort of something that's related to oscillations that we just studied last time. And it's about waves. And waves is such an important phenomena that, I mean, that's why it has been categorized as like a one big stuff that you need to learn. It's like a big topic, right? And it's just a fundamental of stuff that you are going to face later. Like, there's so many waves that you have to deal with: the sound, light, uh, I don't know what else, like water wave, physical waves like strings and everything, or even like in quantum physics, you have like something such as probabilistic wave or some wave function, or you try to understand things using some wave theory, on and on. So stuff over here is going to be so important that if you eventually have to deal with any kind of oscillations, and that oscillations has some interaction with the rest of the environment, you cannot running from it. You have to stuck with waves. Okay, so let me sort of like give you like a grand introduction of waves to be just this sentence right here. That's it. The propagation
Okay.
of a disturbance. It sounds pretty disturbing, I guess. But that's a simple idea of waves is this. So every time that you try to do something, okay, and if that thing has some interactions with the rest, I mean, it doesn't have to be the rest, but some other things, that interaction will eventually propagate whatever you do with the first thing to the second. And if the second thing has some, third things that is interacting to, whatever you passing on to the second will eventually get passed on to the third. Okay, and the process just keep repeating. If the third one has the fourth one waiting and interacting, whatever you're passing on from 1 to 2 to 3, eventually going to get passed on to 4. Does that make sense? All right, so that's what I'm saying is, to think about this kind of thing, you must have a source. Source means you do something with it. Okay, that's why it's called disturbance. You disturb something, and then that thing that you're disturbing, so assume that as your medium, and within your medium, you have like a tiny elements that build up those mediums. And then eventually you have some interactions inside your medium. And that's the third one. You have some sort of like mechanism to which the adjacent portions of that medium can influence each other. So it means you have some interaction that I was talking about. So that means whenever you do some disturbance at some point, eventually the disturbance is going to get propagated. So you have the propagation directions of that disturbance. Okay, so that is wave. Does that make sense? Okay, so I think that's sort of like give you an overview of things that happens all the time. Like when you put like maybe you dump something into a pool, a pond or something, and then you create a ripple. Okay, that ripple, that is the wave propagation. Okay, and what you're doing over here, but you're just dropping something into the water, and that is creating a disturbance. Okay, and if that disturbance, all right, we try to link to something else that we just studied last time. If that disturbance has a chance to do something oscillating, so it means you go up and down, up and down, up and down, up and down, on and on. The wave that we're gonna generate is going to, sort of copy, or at least have some characteristic of the things that you generated at the source. Does that make sense? So that means if the source is trying to do simple harmonic motion, so hopefully that characteristic should show up in the wave that get propagated out as well. So you can guess in your head, oh, Adan, it's supposed to be sine cosine function. See, isn't that cool?
Okay.
I don't know, does it make sense or not? But to me, I think it's a very one-to-one mapping, and it's so easy to just, okay, I think I can accept this concept very easily. So that means if the source doing something, and then that thing in the source get propagated out, the thing that you receive, obtain from the propagation, supposed to have some clue or some evidence of what is going on at the source. And that's exactly what the sound is. Does that make sense? When I'm talking, or when you guys speaking, you create the vibration in your vocal cord and stuff. All right. And that vocal cord interact with the air, and the air gets, sort of like disturbed. So you get a propagation of the change of the pressure around you, because, some get pushed, some get pull, push, pull, push, pull. When you do that sort of like oscillation very quickly, and that disturbance that happens right in your vocal cord and everything in your neck and everything get propagated out. Whatever you're hearing, that's the sound, right? But the sound is going to have, you guys knows that, okay, you generate the sound from here. That's when you sing, when you speak and everything. So the sound that you hear should tells you exactly, not when, if you really want to know exactly, but I mean, at least the sound that you are hearing has to be generated from whatever going on, the oscillation happens inside your vocal cord here. Does that make sense?
Okay.
Okay, so that's it. So that's like a grand introduction of things that going to happen. It's just like you need the source, and the source is supposed to do something about it. But then once it's done, you get propagation of that disturbance. Okay, and the shape or the characteristic of that disturbance, we're going to name it waves. So that means if we can analyze something about waves, we should be able to tell something about the source as well, because they are connected like this. Okay, but all right, the stuff that we are going to do is, all right, Ajahn, I know there are some connections here. However, how are we going to describe waves? Because now we add something to it. You can see that now there is some sort of like a, movement going on, because there is a propagation. So there's no doubt you have to deal with something that is moving. So if something is about to change in time. All right.
Okay.
Oh, that's the wrong sound effects there. Okay, here we go, guys. So just to get you started here, we can classify the type of waves based on the way that it's going to travel. Okay, so first, if you look at the first case, look at this. Now you understand that, okay, there is a source of disturbance, which is the hand of this dude right here. And let's say if he hold on to left side of a spring, and let's say you can think of this one as a string first, doesn't have to be a spring. It could be just a string, all right? But because they try to use a spring, because a spring can do a couple of things that you are going to see. So if you look at this one, and then this guy just move his hand up and down. So this is a source of disturbance right here. And now you can see that you have something traveling up and down over here. Okay. However, because his hand is attached to this spring, so the spring will start to move, and then everyone understand it. You are creating a wave, and the wave eventually will travel out over here. All right. Let me just highlight just the first one. There you go. All right. So that is the direction of the travel of the wave, which is fine. Let me call it V. That is like a velocity of waves or speed of waves. That is fine. But then when you look at this one about John, there is another speed or another velocity that you have to talk about. It's his hand right here. See that? And if we were just to use something that we just learned about John, if his hand is moving up and down in a simple harmonic fashion, why not? Right? Because that's what we're going to do anyway. We don't know what else we're going to do, right? This is the easiest way that we can deal with it. So that means there will be some, if you remember, there is a displacement, there is a velocity, and there's an acceleration, right? Complete whole package over here, because you know how to describe the displacement as a function of time, differentiate. Once you get velocity, you differentiate velocity again, you get acceleration. Does that make sense? So that's it. There is another velocity involved. Let me call it another V. See, so there are two speed that you have to make sure that you understand that there are two things moving right now. Propagation get propagated away. The source is going to keep moving at fixed position. It does not travel with the wave. You have to be able to distinguish this too. Like, of course, I know now to distinguish the two. But once I throw in mathematics, now things going to get more confused over time. So you have to keep this in mind. This is the key stuff. Okay. So over here, as you can see now, I can call this V to be like, okay, let me call it like a V in the Y direction. just to distinguish this one from the V of the waves, the one in the red. So over here, then if you look at the direction of the travel of this velocity or his hand, it's in a vertical direction. But then the propagation of the wave happens in the horizontal direction. They are perpendicular to each other. That's why we're going to name this type of waves the transverse wave. Okay, cool, guys? That's the
Okay.
first type. But another way that we can play with this spring over here is if you look in the bottom figure over here, instead of his hand being moved up and down, he can push in and just, pull out. So it's push and pull instead. So over here, the source have velocity as well, but now your velocity of the source is going in the horizontal direction. Let me call it V sub X. Okay. However, you understand that the propagation of that disturbance is going to travel no matter what. Okay. So that means you're going to still have the wave. Okay. Let me just highlight part of the wave. And that compression, decompression of the spring will get propagated out over time. Where does it go? Well, let's say it's somewhere, all right, somewhere around here, let's say. There you go. So that is your propagation speed. With me, guys? Okay, so now you have two speeds that are parallel to each other. So it means the direction of pull and push and pull are parallel to the direction of the propagation. So if this is the case, then you're gonna name this a long. Oh, it's the wrong color there. You're gonna name this a longitudinal wave. Okay, and now you just like, whoa, now wait a second. So do we have like a separate mathematics for both? The answer is don't worry, guys. Because if I just focus on these longitudinal waves, and I am still saying that his hand still move back and forth in a simple harmonic fashion, let's say. So that means whatever that you already studied back in, the oscillations last time, the sine and cosine function is also valid. So that means you only need only one kind of mathematics to describe both types of waves. Does that make sense?
Okay.
So that makes your life a lot easier because you don't have to worry about, are you going to deal with the transverse or are you going to deal with the longitudinal? Mathematics has the same structure. That's a good thing about it. Okay. However, okay, because you have two types of waves. So in the physical stuff that is actually moving, one has to go vertical, the other one is going to go horizontal, but the mathematics will have the same form. And to be exact, sine, cosine. Okay. What else can it be, right? Yeah. So that's what we are going to deal with today. And to me, I like this one, guys, because what we are looking at over here is, to me, I think this is the hardest part that confuse a lot of students back in high school. Because when you deal with this topic over here, it seems like mathematics just suddenly gets complicated out of nowhere.
Okay.
And I'm not so sure that you guys realize that you are dealing with something kind of complicated in mathematics as well. And that means you are about, okay, I don't know, is that good or bad? Okay, let's turn it off. So it's because you are dealing with two variable functions. I don't know, you noticed this before, or for those of you that, I hate physics in the first place already, so don't worry about it. But for those of you that sort of like struggle with this topic, maybe once or twice in your life, you're probably wondering like, what is going on with this thing? And I hope that I'm going to be able to demystify everything today. And hear me out. All right. And once you get the underlying structure of what we are about to do here, I think the rest of the stuff will be once again pretty clear and easy to deal with. All right. Well, I don't want to use the word easy, but at least you have something to grab onto and then try to attack future problems. Let's take a look. I have a simple question for you. Let's say I generate a wave and just throw away the simple harmonic at this point. Okay, don't worry about simple harmonic. I can create any kind of wave by moving my hand ups and down. Or I can move my hand up, wait a little bit, and then move it down. Or I can just move up, down. You can create any pattern, right? And that patterns will eventually get propagated as the wave. Does that make sense? Okay.
Okay.
And now let's say I just create a pulse. So when I have a pulse, maybe I just move my hand ups and down and I'm done. I don't want to do anything else. I don't want to do simple harmonic motion. I don't want to go up and down forever. So I generate a pulse that look like this. And somehow I have a way to plot this one now using a function because we have a lot of mathematical background. So I can say that I can write a function of this curve. Exactly. I mean, you look at the shape of the string over here that you generate and say, but Ajahn, I'm going to write the function for this. So fine, go ahead. Let's say this is it. So you have y as f of x representing this curve right here. And because you know that this is going to travel, yeah, it's going to move to your right. And let's say, let me call this my time zero. Every time we're doing physics, we probably have to have a starting point somewhere. So let's say, there you go. This is your starting point. The shape of the wave look like this. My question is very simple, guys. What will be the function y at later time t? I don't know you understand my question or not. What will be the shape of this wave when time is at some other time, not zero, at other time t? That's what we are trying to get to. All right. So let me answer this question by doing this. I'm just going to have to add a page here. Okay. Do we need 2 pages? Just one, I guess, enough. All right, guys. Let's follow my logic over here and let's see if you sort of like agree with me. So if you have XY axis, so this is just like before, nothing is new. And then you are looking at just a simple 45-degree line. What is the equation of this one, guys? Well, John, that's straightforward. Y equals to X. That's 45 degree. Now, let's say I have another line that's sort of like 45 degree as well, but it's going to the right side of this one. So look at the green. And let's say I'm going to tell you exactly what happens too. Okay, let's say this green line over here cuts the x-axis at A somewhere. So what is going to be the equation for that green line, guys? Very good. Whatever you're thinking is correct. It's going to be y equal to x what? Minus A. With me, guys? The reason for that is because if you have the x-intercept to be at A, so that means your y-intercept of this green curve is going to be at negative A, as you can see from the plot over here. So the general form of the straight line equation is just y equal to mx plus b. So it's no big deal. M is the slope and the b is just the y-intercept. So over here, I just say, John, you just write the green straight line as x minus A. So let's move on to another one. Let's say if I have another line on your left instead of on your right, and let's say now it cuts the x-axis as B somewhere. So if this is the case, then the y-intercept up top is going to be B as well because the slope is 1, right? Everything is perfect. So your red equation, the blue equation will look like y equal to x plus B. So far, so good?
Okay.
I haven't done anything. It's just a straight line. So this is straightforward. It's easy enough. Now, you guys try this. So I'm going to draw another curve over here. And let's say now, let's move up a bit. Let's deal with the parabolic curve. If I can draw it. Okay, that's not too bad.
Okay.
And everyone knows if this is like a simple parabolic curve, it's going to be y equal to x squared, correct? Now, guys, I'm doing the same thing. Let's say if I'm going to translate this parabolic curve to my right side by a distance a. So this means I'm going to have this curve, like a green one over here, and assuming that the tip down here is going to happen at A. Guys, give me the equation. Oh, oh. Alert, alert. That's my sound effect there. Okay, so give me that equation of the green line, guys. Come on. All right, you don't have to type anything back, just write on your own. What is that? The green? If you remember vaguely, it's like, Ajahn, I sort of already remember that if you want to somehow write the parabolic curve, but it's sort of like the bottom of this curve is shifted, or at least it happens at x equal to a, the shape will look like this. I mean, the curve can be written like this: x minus a, the whole thing squared. Does that make sense, guy? Sort of bring back some memory here. Yes or no? All right, let me do one more. Let's do blue. Okay, if I'm doing the same thing, I'm looking at parabolic curve. Oh, what happened here? There you go. Oh, there you go. All right. It's supposed to touch. Okay. And its tip is at B. The blue curve will have the form of the function look like this: y equal to x plus b squared. You guys with me? So far, so good. So if you sort of like correlate this to something that you have already learned in the past, you might have sort of like discussed this topic under the curve shifting. If you want to translate a curve, like there are two choices. You want to translate horizontally. So this is what happened. If you would like to translate horizontally, if you translate to your right, you subtract out the distance that you are translating. Like for this one, you can think of it like you start from the red, you translate to your right side to the green by a distance of a. So you take the original function, x squared, and then you turn x into x minus a. Okay? Same thing happens if you want to translate the curve to your left. In that case, you just change your variable from x to x plus. And in this case, you translate by a distance of b. So the whole function will go like a plus b, the whole thing square. Cool? So that happens over here on the left as well in the straight line, see? So when you have a straight line y equal to x, when you translate the red line to the green, you translate to your right. You change x to x minus a. If you translate from left to, from right to left, so you go left hand side, you translate by a distance of b, you change x into x plus b. Right there. Cool? So far, so good. Now, I don't want this. This is sort of like boring because it's just a sort of like a fixed translation, right? I want an animation. Whoa. Can you give me an animation of this curve? That is going to be the stuff that we need. But what do you mean, Ajahn, the animation? So let me start by writing this axis one more time. And now let me start from that, curve again. It could be parabolic curve, that is fine, but it could be any function now. Oh, sorry. So let's think about this is y, which is a function of x, and this is x squared, right? Now, I want an animation. I want an animation. What does it mean, an animation? It means what I'm wanting is just like, I don't want just a fixed stuff. Let me play with this a little bit. I want this curve to travel in front of you like an animation, traveling, going, just passing you by. So what I want is I want this thing to actually traveling. Seriously. Okay, I'm still having hard time trying to understand this whole thing. I don't know. This is so weird to me. All right. Okay. So what I want over here is I want this thing to travel. I want it to travel. I don't know. How could it be? How can I make this travel to my right side? Move. I want it to move. Think of it like an animation here. Not like it's fixed or, just like a shifting or translating. I want it to travel. So that means you have to introduce a concept of time, right? Because time keep moving forward. And if you put some function in time in it, it's going to give you animation because time keep going forward. So the idea is very simple. Well, guys, back in here, when you are moving from here to there, instead of having a fixed distance a, you put it a function of time. So that means if you think about it, let's say at some time t, you say, hey, I want to stop right here. I mean, I'm supposed to be at the X mark position there. So it means it's going to already travel by this distance. And then say later, it's going to keep going to your right, 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 to your right in time. So the thing is, you have to ask me back how fast you want this X mark to move. All right. I would say give it a speed V. Let's say I want it to move to your right side at the speed V. Well, Adan, okay, once you give me the speed, I can figure out for you where should it be. You just take the V multiplied by the time. Yes?
Okay.
Oh, there's some, okay, pretty close. X, all right. Getting there, getting there. Yes. So that's it, guys. So what you want is instead of having the A plug into your original function and do that translation, you replace it with VT. Yes, with me?
Okay.
So that means all you need to do is just turn this into VT. And if you have the negative sign in front of it, it means you are traveling to your right side. So that means that it's going to be X minus VT squared. With me, guys? This equation will be the parabolic curve that actually moving to your right at the speed V. And once you want to know where is it, you just plug in the time. And then you know exactly where the curve should be. And this is where that difficulty just popping up. See this? Now you are dealing with two variable function, guys.
Okay.
Without knowing it. I don't know, probably. But to me, this is, you're going to have to write this one as f of x and t. Of course, over here, you don't need t because you assume that that is happening at t equal to 0. So t will just disappear from your equation all over everywhere. So that's why you can still, deal with x alone. But now you want an animation. So if you want an animation, there's no way that you're going to avoid time. Now, if you want to do the same thing, but I want this thing to travel to my left instead of right. Now things are going to be easy because that equation will look like just change the negative sign to a positive sign. Cool. All right. So once you get this point, come back and answer my question here, guys. So let's say somehow I have a way to write this curve as a function of x at time equal to 0. But of course, everyone knows this is a wave, so it's going to have to travel. And let's say if it's going to travel to your right with the speed v, what should be the shape of this curve at later time? Bam. Got that one? Woohoo, you done.
Okay.
Does that make sense? So all you need to do is you just substitute x with the x minus vt if you want this curve to travel to your right. And of course, Ajahn, if I want this to go to your left, just pick positive sign and it will travel to your left. And it's an animation, waves never stop. Once you generate a wave, waves will keep traveling until it dies away or whatever. If there's no friction and anything, it's going to travel into the edge of the universe, whatever.
Okay.
Okay. But that's what it is. Okay. So that's why, the butterfly flap its wings in Argentina and generate like whatever the storm in Bangkok or something like that. That kind of like, statement over there. All right. So waves generate somewhere. I mean, it's get generated somewhere and it's just propagated out. All right. So that's what it is. That's the whole, I mean, it sounds like tedious and long. I mean, I know I spend a lot of time just explaining this translation stuff over here, But it turns out that's so important, guys. Unbelievable, all right? That once you get this one down, the rest is going to be super, super straightforward. Okay, so here's the conclusion. So once you have this, whatever function that you got in the first place, f of x, okay, now you can make an animation out of it by just, all right, if you want to get an animation that traveling to your right side, you subtract vt. And if you want to get an animation to your left, that is going to be plus vt. Okay, and because this is going to be the two variable function, then we're going to have the wave function. So now in your head all the time, wave function is always two variable function, space and time. And of course, every time that you cut down that t, so it's mean I don't want to deal with time. I want like a fixed, shape of the waves. So that means, think about it, wave never stop. So the only way that the waves can show up in your textbook, right, or on the screen, you just have to take a photo. You just take a snapshot of it. So once you take a snapshot, it's the same thing as you substitute t somehow, somewhere. Once you draw the curve on the screen, see it in the textbook and everything, that means you take a snapshot. So you freeze the time. So when you freeze the time, you eliminate from the two variable down to a single variable. Okay, oh, sorry, just keep the screen to refresh a bit. So when you have like a snapshot taken, so you're starting from two variable, you sort of like get rid of the t because you already, you probably can tell, hey, I'm going to take a photo at what time. So your function reduced down to a single variable of x again, and we're going to name this one waveform because that is the form of the wave. To take a photo, you know exactly what is the shape of the wave. Cool?
Okay.
If that is cool, guys, answer me this. Give it a shot, guys. At time equal to 0, a transverse pulse in a wire is described by the following function. X and Y are in meter. The function of X and T that describe this pulse at other time, okay, what should it be? That is the question. Let's apply it, guys. Somehow I know the waveform at time 0. It looks like that. And if somehow you know that, hey, it's traveling in the positive x direction with the speed, oh, wow, that's good.
Okay.
The speed is given to be 4.5 meter per second. What should be the wave function at any time? I know you guys, I think I know you guys know the answer, and you wouldn't believe it. It's gonna be x minus, because it's gonna travel in the positive x direction, right? The speed times the time. The whole thing still keep the same function form, just like original. You are done.
Okay.
It's that simple. Seriously, guys. It's that simple. You are now having in your hands a traveling wave pulse. And now you can substitute time. You know exactly what's the shape of the wave should be at any time. Cool? Next, try again. If you are given some crazy form of the function, doesn't matter. This one is like exponential, blah, blah, blah. X is in meter, T is in second. Answer the following questions. The direction of the wave motion, guys. You guys still with me? เฮ้ย okay อันนี้ไม่ได้อยู่คนเดียวนะ Okay, the direction of motion, you only have two choices. It's either positive x or negative x, right? Perfect. Very good. That is going to be negative x. Or, I mean, if you just use a standard left-right thing, it's just going to your left. If you say the right is a positive x. Cool? See? Easy. Second, what is the speed of the pulse, guys? Whoa. Wajan, just zoom in. Whatever the numbers that shows up in front of t. Yeah, correct. 5 meter per second. Everything is in SI system. You are done.
Okay.
I think you won't believe it's that simple. And the key is you don't even have to care what's the function that describing that waves. You guys seeing what I'm seeing over here? It doesn't matter. This like crazy. This is actually, if you can relate this one to, this is like a bell shaped curve, like a normal distribution curve. That's what it is. Okay. But it just, the key point is it's already in the form of x plus or minus vt. Any function that is being written under this function form, x plus or minus vt, it's a wave, guys. Yes.
Okay.
That's simple. Okay, that's a question. Does wave carry energy? That's a very good question. Answer is definitely yes. Because when things get propagated, it has to carry along the energy. Otherwise, that medium will not be able to move. With me, guys? So actually, energy is exactly has to get carried along with the waves. So we're gonna have, time to discuss that for sure. Yeah, but your understanding is totally correct. Yes, energy is get propagated along, even though we name those stuff like disturbance, but something, energy has to be the thing. Yes, cool. All right, get going, guys. So now we are going to combine the two together. The one that we studied from last time, the sinusoidal waves, came from the simple harmonic motion. Yeah, up and down, up and down, up and down forever. And then let's say if that is your hands moving up and down, and your hand is attached to a string. So the string is going to oscillate and generate the wave in the sinusoidal form as well. Does that make sense? Okay, so you guys ready? I am going to talk about this and then we're going to take a break after this. But you will see that if we're just going to sort of like, strict and just limit our waves to be just like a sinusoidal waves, thing is going to be now super easy now. Or I wouldn't use the word easy, but it's going to be straightforward now. Let me add another page here. And you guys will definitely happy with the result, I hope. All right, guys, remember from the simple harmonic, that's your general form or the general solution or whatever things that you need to solve that Newton's law, which is like, okay, John, we remember y as a function of time. Oh, let's look at the form of the function there. Just make it simple. So because right now I'm going to write everything under the x-axis. So let's talk about the function of x. Okay, so let's think about x for now. And then I have a sine. Let me call like some constant k and x. So this is look pretty close to what we had last time, even though last time the function that you are writing is a function of time because you try to time your movement, right, to get to simple harmonic motion. But now, because we are focusing on the shape of the disturbance, it's going to get moving away from it. And it's going to have a shape of this curve over here. So the orange curve that you're looking at, that is the waves coming from your hands, simple harmonic motion. So the assumption is the oscillation of the hand will translate into the sinusoidal wave function. All right. So I am going to write that the orange sinusoidal curve for you. Okay, guys? Okay, with me? Right here. A sine kx. Pretty cool. Because you say, okay, let's say this probably have some amplitude A. And the K is just there just so for you to be able to adjust the distance between peak to peak. That's all. So that's your general equation right there. Now, guys, give me the blue. I want this orange sinusoidal curve to get animated, travel to your right with the speed V. Go ahead, guys. No, you don't have to write it down. That's it. I'm going to write it down like this. A sine K. All I'm doing is just X minus VT. And I'm going to write this one as like X and T function. You are pretty much like 50% done. Isn't that cool? So now you have a translating sinusoidal wave that is moving with the speed V. All right, now I'm going to show you next what could happen from here. So from here, now, every time, if you start from the blue and you take a photo, bam, you get a waveform down here. You guys with me? Okay. So every time that you look at the wave, and then when you see that your x-axis is just x, is the position, So this is actually your snapshot of a real wave, because a real wave never stops moving. The only way that you can capture that into the screen over here, you have to take a photo. So everything is under X. So you can define a couple of parameters to describe the character of this wave. The distance between 2 points adjacent to each other that look alike, look exactly the same. For example, peak to peak or the bottom to bottom, we're going to name that distance wavelength, the lambda. Okay. The other one you have already learned, the height of the wave, we called it amplitude. So far, so good. All right. But now, because you are dealing with two variable function now, so you have another choice. Instead of picking the horizontal axis to be space x, so space x is not Elon Musk, space x. Instead of a space variable, you can do the time by freezing the x instead. You guys with me? You see what I'm saying is, if I have this equation over here, and let's say I am going to pick the x, well, hey, I'm going to freeze the x. Let's say x equal to 0, for example. So now you're going to reduce your function down to a function of time instead. A sine, okay, let me write it like k minus vt, yeah? All right, don't worry about the sign at this point, but the idea is x will disappear from the equation, just like when you take a photo. When you take a photo, you get rid of time. When you freeze the x, you get rid of x. The only thing left for you is time. But what does this mean? This go back to the simple harmonic motion that we studied last time. Remember? When you have a function of time that is sinusoidal, all you have to do, all you're looking at is just something that is moving in time. So here, let's imagine that you are in the ocean, or you're going to the sea, and then you are sort of floating on the surface of the water. And there is like a wave coming in, okay, the water's wave from the ocean and stuff. And you just like, just floating around. The wave hitting you, the only thing that you're doing is just you moving up and down. Does that make sense? You only move up and down. The wave just passing you by, but you are just traveling up and down. Of course, in reality, you probably, go back and forth a little bit. But anyway, in theoretical world, the water's wave that's going through you, right, going to take you up, bring you down, take you up, bring you down. Is that what it is? You are staying at the same position, but your body is traveling up and down. That's exactly this function right here. So if you take your position, which is now vertical, and plot a curve where you are, you're going to go up to the top, down to the 0, go down to the -1, back to 0, go up again, and plot the curve. You're going to have this curve right here as a function of time. With me, guys? So you have to be careful over here that every time that you're looking at a wave that being plotted on an axis or on the axis over here, you have to be able to now, you have to notice, you have to observe now that the horizontal axis is representing x or t, because you are dealing with two variables at this point. And once you see that, okay, John, the x-axis is t, it means you are stationary at some value of x. X is being fixed. Cool? All right. But once you fix that one and you plot your displacement that you move up and down in time, now you can interpret just like what you did with the x variable. If you look at two positions that look exactly the same but adjacent to each other, the distance between these 2 points will be in the function. It's a time, right? The unit is time. So that is the time that it takes for you to complete one cycle. So that is your period. Make sense? However, your amplitude stay the same because you still, you still have to move up and down in the vertical direction. So that won't change. But at least you can see that to be able to write this one, you have to fix your position first. That means you have to eliminate one of the two variables out from your equation. And then the concept of the frequency and the periods is exactly the same as before. So we can still use that. And here comes the final conclusion before we take a break right here. So come back here, guys. So now we understand that this whole thing, okay, this blue thing This is your sinusoidal wave function. Isn't that amazing?
Okay.
Simple. X minus vt is already built into this equation. You are done. You have an animated sinusoidal waves. Okay. And the second thing I want to throw in just this point here is now when things get sort of like parameterized as a lambda, as a time period t, the concept of the velocity now can be written under these two parameters here, because you know that the wave will travel this far, one complete cycle will take one period of time. You guys with me? Because one period of time, the wave will cycle it through, I mean, it will go through the whole cycle, one full cycle. But during that time, it's going to have to travel already one wavelength. So actually, you can write the speed of wave taking the distance over time, right? Concept of the speed, distance over time. But you guys know all the time, and you already knew that if you travel by a distance of one perfect wavelength, it will have to spend exactly one period of time, the capital T. And then because the capital T is just inverse of the frequency, so you can write down V equal to F lambda. You probably have heard of this formula already.
Okay.
But that's just a straightforward derivation of this V equal to F lambda. It's not like a special formula for waves or anything. It's just distance over time. And because you travel one wavelength using one period of time, and period is just the inverse of frequency, V equal to F lambda. Okay, guys, take a break right here. We'll be right back. A lot of fun is good. All right, so once we have already seen like how we can parameterize a couple of terms that we're gonna be able to use it time and time again, the lambda, the wavelength, the amplitude is just the height of the whole translations of the medium, the period and frequency. And now we get to the products between the frequency and the wavelength, give you back the speed of waves, all right? Keep in mind all the time that the velocity that we are talking about over here is the speed of the wave. See, don't forget the wave is traveling to your right, never stop, it's just keep going. However, there is another movement that we have to make sure that we understand that actual movement of the medium, you are floating on the surface of the water, but you are not going along with the wave. With me, guys? All right, you are not serving the wave or anything. You are standing still. I mean, you are stationary at a fixed position, but you only move up and down. So that means you must have some vertical velocity going on with it. Okay, let me call it subscript y for now. So you are looking at two velocity in one because we are having an animation. Cool. All right. So keep that in mind. Now, this slide looks sort of like what, no, it was already nice and cool, but how come it's get complicated again? And eventually there are a couple of arrangement that we can do, or even though that's how the textbook usually will try to write things down. But what I'm going to show you is just go back to what we had and we just extract those things from what we already understood, making an animation out of just a sinusoidal wave. Okay, shall we? Okay, let's take a look at this one. Let's jump up here first. What should the K mean? That's my first question. The K was introduced just for you to have some parameter that you can adjust, the shape like here. So think about this one. If you have sine X, this is sine X. So if you sort of like squeeze in, you want something that is, oh, that's not good. Here we go. Here, all right. So that means for you to be able to see this, it takes this whole distance over here to complete one cycle, right? This is your lambda over here for the red. But if you look at the green, your lambda of the green is only this small over here. See? So it's sort of like squeeze the wave to be more compact. Okay. So how can we draw the equation for the green one with respect to the red one? Because you have already seen that the red is sine X. But this one is half of that. It takes only a smaller portion of X to accomplish the same value. Does that make sense? Okay, so that means you don't need the big value of x to get whatever the red gets. You only need like a smaller to get to the green. So what I'm saying over here is it's supposed to be 2x. That was what the k is about. Okay, so that's mean by adjusting the numbers in front of x, that's how you squeeze or you expand the shape of the sinusoidal wave in the horizontal axis. Does that make sense?
Okay.
Okay. That's the wrong sound effects there. Okay, so that's why the K is telling you something about the lambda. The K is supposed to be able to showcase something about the wavelength of the wave. And what's exactly that? So now you take into account the whole thing about the wave. We already discussed this many, many times in trigonometry. Every time that your argument in the sine go 1, 2 pi, that means you complete one full cycle. Does that make sense? So that means you can take that parameter there. I mean, that whole thing there, kx. Okay, let me put the rate here, right there. So the kx, once it's want to get to 2 pi, how long of the x should it get? I mean, what should be the distance of x that eventually you can revolve your cycle to complete exactly one complete round? Well, Adan, you need x to be one perfect lambda. That's a parameter that we just said. We call the distance that you complete exactly one full cycle. That's one wavelength, a lambda. So that means k is just 2 pi over lambda. Does that make sense? And that is the relationship between the k and the lambda. As you can see, the bigger the numbers k, the smaller the wavelength, just like you saw between the red and the green curve. See, the factor in front of x right here is, you can think of it like 1. But the factor in front of here, it's, I mean, you squeeze down your wavelength to half the size of the red. The green is half the wavelength of the red. So this is the reason why the numbers in front of the green has to be double the numbers in front of the red one. Okay, cool?
Okay.
Okay, so that is the definition of the K. The K is connected to the wavelength through 2 pi over lambda. Nice. Move on. Next, look at this one. Hey, Ajan, what about the factor in front of time? We have already seen that you can see that whatever that goes show up in front of t will give you the speed of waves, correct? But I can manipulate this one just a bit further. Follow me here. So let's say I'm just gonna distribute that k inside, okay, going from, actually I should use the blue, guys, sorry, because, so here we go. So just come here. So what I'm going to do is it just say a sine. I'm going to distribute the k into inside the parentheses there. I have kx minus kvt. So far, so good. But now we already learned that the k is 2 pi over lambda. So actually, I can do one step further. Okay, keep the k, the x, 2 pi over lambda. So far, so good. And now you already sort of like, okay, done v equal to f lambda as well. So I'm trying to manipulate this one to make it look like this, guys. Kx minus, there is a 2 pi f, because lambda would get canceled. Bam, bam. And remember what the 2 pi f is for? Back in the day of circular motion, simple harmonic motion, everything are all related now. 2 pi f is just the angular frequency. So we will be able to name this one. Let's call this omega. Okay, let me use the black one here. Let me call this omega. So that's it. So you can also write your wave function in this form right here.
Okay.
And so, because you know that the omega is 2 pi f or 2 pi over period, you can also write it like this. Okay, you guys with me? Sort of. Same thing.
Okay.
So I hope from now on, every time that you read the textbook about the waves or whatever, and then you have to deal with the sinusoidal waves as a two variable function like this, you won't get confused anymore. Each textbook will write this wave equation or wave function in a different style, depends on what they like. Okay. But the main two style that usually we will be able to spot in the textbook, it's either kx minus omega t. That's one way of doing it. Or you can say 2 pi x over lambda minus 2 pi t over period. So they're both nice. Okay. The left side seems very compact and you understand what the K is, you understand what the omega is, everything is good. On the right side, it show up some sort of like a, you can say like a symmetry of the equation a little bit. The first term giving you the idea of the ratio between the position X with respect to the lambda. See that? So the ratio that I highlighting over here will give you like a fraction. You use like, okay, how many, the distance that the wave is at can be treated as how many lambda. And you guys know that every lambda will be equivalent to 2 pi. So all you do is just taking like a ratio. Every lambda will be 2 pi. If you have x equal to 2 lambda, that would be 4 pi. If you have x equal to 3 lambda, that would be 6 pi, on and on and on. Does that make sense? Same thing happened with time. Because everyone knows if time has already gone by 1 period, that will be equivalent to 2 pi factor. And if the time is like 2 times a period, that would be 4 pi. If the time is 3 periods, that will be 6 pi, on and on. So this form of the function will give you some sort of like, it's just like a simple taking the proportion and how would that proportion of space and time eventually will get into the argument of the sinusoidal function over here as a radian, right? As an angle. Does that make sense? Very good.
Okay.
And there's a question here. Is it the same as the omega equal to square root k over x? That's really, okay. Here we go. That's a very good question. What you learn over there, that's the connection of the omega to the physical system. Okay. So over here, we are only looking at the wave that's coming out of it. You see what I'm saying? It okay right now. Okay, just to be clear. So think of it this way. So let's say the root k, actually it's supposed to be root k over m, guys. Not root k over x. All right, but anyway, I think I got you. Okay, so root k over m, right? I think I'm talking about the same thing here. So the thing about this, if this black, that's blue, okay, blue dot over here turns to be just the mass m that we learned last time. Okay, make sense? And this mass is attached to the string to the right. And it turns out this mass is like a mass attached to a spring that is oscillating up and down. So you will explain the oscillation of this mass with the omega equal to root k over m. Does that make sense? But then because of this mass is attached to a string, this oscillation of this mass will generate a wave traveling to your right. And that wave will be sine, okay, A somehow amplitude sine kx minus omega t. Yeah, so far so good. But this omega will be exactly the same as this omega. So when I say, does it related? Yes, because now omega that you will put into this wave equation must come from the source of disturbance. And because if you use that omega equal to square root k over m, it means you use the spring and the mass system to be your source of disturbance, then yes, you can use that omega and plug it in here. Does that answer your question here? ทุกคนเข้าใจไว้ด้วยเนาะ Okay เนาะ Okay, very good. All right, so that's a very good question because that's sort of like confirm the point that I started this lecture with. The waves will give the evidence of what is going on from the source, at the source. Okay, the source doing something, it must, leak that thing or information out in the waves. Can we find the wave's position at a specific time? Can we find the wave position at, yes, you can. Because this equation here is already both a function of space x and time t. So if you really want to know exactly where the waves, or I mean, when you say where the waves mean, where the waves has already traveled and where should it be at whatever time, you just plug in the t, plug in the x. I don't know, does that answer your question or not? Yeah, okay, I think. All right, good. So because this is complete description of this wave, so all you need to know is just, okay, where you want to figure out, plug in the x. When you want to figure out, plug in the t. And once you plug it in, you know exactly what will happen to the medium. And that will be the last part of this today's lecture as well. Okay, that's a very good question there. Okay, all right, guys. So now I hope you understand that it's just the derivation of, I mean, it's not a derivation, it's just like a manipulation of the shape of the whole function that we just already wrote just right before the break. And we just rewrite it in other maybe more convenient or more obvious way that showcase the sinusoidal waves down here. Okay, and that conclude, here we go. From now on, even though it looks so bad at first, if you look at these two slides over here, yeah, and then this derivation that I put on the slide over here just came from the textbook. It might find it, you know, tedious and stuff, but I mean, at the end, we know what the k is. K 2 pi over lambda. That is a special name for this. We call k the wave number. No bad. All right, that's fine. All right, we can name it. That's okay. And omega, as usual, 2 pi f. Okay. And now, once you read this one, you won't feel afraid of this form anymore. Look at the first one, guys. The wave function is the a sine k x minus omega t. And now you can add your initial phase or the phase constant wherever you want. We already agree with this. Whenever you deal with the sinusoidal function, that's when you want to start the whole thing with. That's your phi right there. Or if you want, you can write your wave function in terms of 2 pi, and then you take the ratio between x and lambda, time and the period, and then that's it, you're done. These two are two equivalent form of the same thing. They are sinusoidal waves. And that completes how you describe sinusoidal waves. And actually, that's all you need, actually. Seriously. Because whenever you study waves, every time, I think I can say every time, you have to start with this, because the sinusoidal function is a fundamental function for everything else. Yeah. Okay. Seriously. Yeah. Okay, guys, let's give it a shot and see, you know, test your understanding a little bit, and you will see how simple this thing is. It's just like you know how to read the wave function. There's no calculations much. I mean, not much. There's no integration. There's no differentiation much at this point. All you need to know is just read. Okay. And you just, okay, once I know how to read this one, I know what the shape of the wave should be. Here, ocean waves with crest to crest distance of 10 centimeter. So that's just peak to peak. That's fine. So what you are having right now is your lambda is 10 meter. See, peak to peak. Then you have a full form. Your wave function is already written down here. What is the wave number, guys? Now you can go back, and this is like original form that we learned since the beginning. Yeah, this is even before you distribute the k inside your parentheses. So this one is actually even easier. So I can just say right away, k is 0.63. Okay, and what should be the units of the wave number, guys? Because by definition is 2 pi over lambda. So the unit of this one should be 1 over meter. Make sense? Fine. So that's it, meter to the -1. What should be the velocity, guys? Oh, then this one is still in the original form, x minus vt. So right away, v is just 1.2 meter per second. See?
Okay.
That's how simple it is. Just read it. See, what is the angular frequency? Well, no big deal. I mean, there are so many ways that you can deal with this now, because you know the k, you know the lambda, you know the velocity. So you can think of it like, okay, John, I can do omega equal to 2 pi f. And then I'm going to figure out the f from v equal to f lambda. So f is just v over lambda. And because you know the velocity is 1.2, the lambda is 10 meter. So that's it. So it's just 0.12. And then you just plug f into here. So you say it's 2 pi 0.12. You're done. Okay. Or you can say about Ajan, I can look at this one, and then because I already know that the whatever the numbers that shows up in the front of the t will give me the omega. So follow me here. So if I rewrite this one myself as 0.63 x minus 0.63 times 1.2 t, yeah, whatever numbers that shows up in front of t, that will be my omega. So I can call this my omega as well. Cool. All right. And it will be exactly the same as this one. Why? I have one more for you guys. I can do this too. Ajan, v equal to f lambda, but the f with the 2 pi you call omega. So what I'm doing is I just multiply by 2 pi divided out by 2 pi. I haven't done anything. But then I'm going to call this 2 pi f to be my omega, and the 2 pi over lambda, that will be my k, correct? So that means another way of writing v equal to f lambda is you can write it as the omega over k if you want. So that means your omega is just v times k. So you can take the results from part A and part B, multiply, then you get the omega as well. 0.63 times 1.2. Does that make sense? Okay. All right. So as you can see, same results right there. Oh, I should use the blue. There you go. Same. All right. So either way, everything works. Okay. Because now your information is just like, all over the place. So it depends on your approach. Use your whatever your preference. But I'm not sure. I hope that the number is sort of like worked out fine. I don't think we need this 10-meter information even, because you already got the equation down. You should be able to calculate the wavelength out of that. And I hope that the 10-meter is exactly 2 pi over 0.63. If not, it would be bad. Oh, shoot. It could be bad. That doesn't look right, is it? Oh, is it close? 0.63. 2 pi. Yeah, maybe. All right, we'll just work it out. But anyway, you guys know what's my, here's my point over here is just there's so many ways that you can get to the omega now, right? It depends on which approach you want. Now, part D, sketch the, when I have the sketch, don't worry.
Okay.
I'm not going to ask you to sketch anything because, you should be just plug into, you put this in a Google or Mathematica or whatever and do the plotting. Everything will look nice and cool there. All right, so don't worry about sketching. But the idea is, if you would like to get a waveform at t equal to 0, all you have to do is just think of it this way. Just plug in 0 into your t value. So look at this. Just want to emphasize one more time. This is what you're getting. See? The t will just disappear from your equation. So this is exactly what we talked about as take a photo. This is a snapshot of the wave. So when you say you want to take a photo at t equal to 0, you get rid of the t. And this is the waveform that you get. Okay, and then you say, okay, at time equal to 2 seconds, I'm going to take another photo. You just substitute t in there. You get exact same wave, but it's going to get translated a little bit on and on. Cool, guys?
Okay.
All right, so I hope you get more comfortable dealing with this waves business over here. Let's move on to the next. Okay, now, so once you know how to read it, okay, so back to my original question or original note saying that, oh, hey guys, don't forget, we have two things moving right now. The wave itself is traveling, the medium itself only oscillating. You guys with me? Okay, so this is once again just like what your friend just asked about omega equal to square root k over m. This is exactly the type of the scenario over here. If you have a string attached to the tip of a blade, And then you sort of like set that tip of the blade in motion. So you can think of this one, the blade just, oscillating up and down, up and down, up and down. So you can think of this dot over here is doing, it's about, it's actually doing the simple harmonic motion. Okay. Up and down, up
Okay.
and down. But because of the tip is being connected to a string, so the string eventually will send off that simple harmonic waves. Yeah, and then we have it as a sinusoidal wave over here. So the wave will travel to your right. Okay. Now, if you are focusing on one part on a string, look at the black dot point P right there. That is you floating on a string. You will only move up, down, down, and then you're going to complete the circle again, up, up, down, down, up, up, down, down. The only thing that you're doing, you are point P. You are only move up, down, up, down, up, down. You will have your own velocity right here. Okay, guys? Just to distinguish between these two, we have been doing this all along. I'm just going to put subscript there. So the V without any subscript, that is for the wave propagation. With the subscription Y, that means that is your vertical velocity, because you, as your point P, you are point P, only move up, down, up, down. You're going to have velocity, but not only velocity, you will have acceleration, because point P will also do simple harmonic motion. You guys with me now? So in conclusion, every point on the string eventually will do simple harmonic consecutively. And that's propagation will just set each portion in the string in the simple harmonic motion sooner or later, right? If you go further away, just wait a little bit, the wave will get to you and eventually you're going to move. And that's go back to answer your friend's question. That's when the energy gets transferred to that point. So that point will start move up and down as well. Okay, guys, with me? So what I would like to conclude over here is, from the things that we have been doing all along, you get the amplitude from the wave function, you get the lambda over here, you get the omega, you can get to the F, you can get to the T from there. All of the information of the wave V equal to F lambda, and this is equal to omega over K. See, everything is on your right side of the equation. Okay.
Okay.
So my question is, once you plug in the X, plug in the T, you just asked me like minutes ago, when you get a number, what that number is. Number is the displacement. Okay, don't forget the whole original point of what we are doing over here. We are describing the waves, but the waves is actually the real movement of the medium. So think of the black dot on the right side over here, the point P. So when you're at that position over here, so now turn blue here, all you need to know is, hey, what is the X value? What is the time? Once you plug in the time and the position, you will know exactly where the point P should be in a vertical direction. You guys with me? In the vertical direction. You never go anywhere. You are only floating. Think of it like if you are in the ocean, right? You cannot go front, back. You cannot travel anywhere. The only thing that you can do is just up and down. Same thing with the string over here. Point P will never travel along with the wave. Point P only oscillate up and down. So every time that you substitute X, you substitute T into the equation, you solve everything, plug in the A, do the calculator, everything, you get the Y. The Y on the left side telling you the displacement of point P. When they say point P, I mean that's point X, right? That's where the X is. Yeah. So that's what it is. So Y, we can say conclusion. Don't forget the whole business that we are doing over here is the vertical displacement. Cool?
Okay.
I hope you got it. And I think this is the part that is getting the most confusing back in the day of like maybe first introducing the topic of waves, because you are dealing with two variable functions, and the waves itself get everything done just by using just the right hand side of the equation. You get all the information about waves already. And don't forget about the left side is actually, it's an actual movement of the medium. Okay. So once you have that down, then the rest is going to be easy. Now you want to know how fast point P is moving up and down. What do? You just take the derivative of this to get to the velocity, because the velocity is just the first derivative of the displacement. However, because now you are dealing with the two variable, so you want to just take derivative with respect to time. So that's why we have to introduce the partial derivative. When I say partial, means you treat x just like just a number. You don't care because you already fixed the position. You only take the derivative with respect to time. And what you get at the end, you're going to get a vertical velocity, or we're going to name this a transverse speed, just to distinguish from the speed of waves. Cool. And the interpretation stays exactly the same. Whatever the number that shows up in front of sine or cosine function will be the maximum value possible. So that's it. So the maximum speed is omega A. But then you say, but Dan, I knew this because this is exactly the maximum velocity that you got from the simple harmonic motion. It has to be, because the point P here, point P over here is doing simple harmonic motion of its own. Okay. But it gets set in motion by having the wave arriving to point P, and then point P will, start to move right there. Cool. พอรู้เรื่องไหมเนี่ยวันนี้ All right. Okay. And if you want to get to acceleration, you just do it one more. All right. So if you do another derivative from that velocity that you got, then you will get a transverse acceleration. Just you have the transverse word just to emphasize that everything is just going in the vertical direction. And the good thing about this one is, and every time you see this, you have the cosine function there for the velocity. And then when you go back here, you have the acceleration, have the sine function there. So it seems like there is a way that you can pretty much eliminate that, sort of like a bad looking sine cosine function, and then just get rid of them all using the sine square plus cosine square equal to 1 thing. So what you do is you take the displacement expression, square it. You take the expression for the speed, the transverse velocity, square them. Then you get the sine square and cosine square weighting over here. And of course, what you can do is you just say, hey, sine square plus, okay, let me call sine squared whatever plus cosine square of whatever is going to always be equal to 1. Then you can arrive at this equation over here. All right. So this equation, what's so good about this one is just give you the connections between the displacement in the vertical directions directly to the speed at that point right away. That is nice. Okay. So that's just like a shortcut. Think of it that way. Okay. By having this, then you don't have to go through the sine and cosine. Don't have to worry about the, crack the whole kx minus omega t on and on. Okay, guys, sounds good?
Okay.
All right, that's not bad. That's not bad. So we will be able to utilize this equation from time to time. But the good thing about this equation is make it so obvious that what is going on in the simple harmonic motion, guys. With me? All right, this is going to sound or look ridiculous, but think of it this way. All right, you have, all right, mouse one again is kind of like nice, easy to see. If this whole thing going simple harmonic across the screen right now, this is so weird. All right, I should have more a better animation over here, but I tried it before, but the animation through Zoom is really bad. It doesn't track so well. Okay, so over here. So everyone knows. I'm going to exaggerate. It's not exaggeration, but you have to imagine that it's not going to go smoothly like this. When you do simple harmonic, it's going to woo and stop. It's woo, 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 like that. You see what I'm saying here? So that means at the turning point, that mouse is going to stop for a fraction of time because it's going to turn the direction of motion is going to come down. And at the bottom, it's going to slow down and then go to 0 speed, and it's going to flip the direction and go up again. So that's why at the amplitude, either the top or the bottom, the speed of this mouse is supposed to be 0. Make sense?
Okay.
And look at this equation over here. When you substitute y equal to a, v in the vertical direction will be definitely 0. See, that's a connection there. And on the other hand, when you go simple harmonic, is a vroom, vroom. So this mouse is going to travel the quickest, the fastest speed is going to happen at the equilibrium point in the middle. Vroom, vroom, and stop, vroom, and stop right there. Vroom, and stop. So that's mean if you try to substitute y equal to 0 into this expression over here, you're going to get omega, oh, sorry, v sub y is going to be equal to omega square a squared in under square root, and that is omega a. Does that make sense? So it just emphasizes that the speed is going to get the quickest at the equilibrium. Is a boom, stop at the bottom, and then you go fastest again at the equilibrium. Boom, when it go up, stop, and come down, stop, on and on. So this is a very quick way of getting the speed at any other point along the way. You can just substitute y into this expression. You get the velocity at that particular spot. Cool?
Okay.
Nice. See, so this is not too bad once you understand the underlying mechanism over here. Okay, guys. So let's attack a couple of exercises, and I think just make sure that we understand what we have been doing so far. Okay. So we have a string is as in the previous slide is driven at a frequency of 5 hertz. So you can think of this one as your F now. That's frequency. The amplitude of the motion is given to be 12 centimeter. When you say amplitude, that's your A. So put it in the SI system right there. And the wave speed, good. They emphasize this is a wave speed. So we use V. So V is 20 meter per second. Units is good. Now determine the angular frequency and wave number for this wave and write an expression for the wave function. So let's attack the easy one first, guys. What is the omega? Omega is 2 pi f. So the f is already given to be 5 hertz. So it's 2 pi times 5. And that's 10 pi. All right. If you want to put the unit in, it's going to be radian per second. Cool. Next, what about K? Wave number. Wave number is 2 pi over lambda. All right. However, that's no big deal because you already know the omega or the F and the V. So once again, you come back here, V equal to F lambda, or you can use omega over K. So that means your K can be found from omega over V. So what you can do is instead of going through 2 pi over lambda, which you can do as well, I can just do the omega over V. Omega we just found up there to be 10 pi. The velocity is given to be 20. So that's it. Your wave number is pi over 2. You are pretty much good.
Okay.
Once you have the omega, once you have the K, write down the expression for the wave function. Okay, John, no big deal. Amplitude. Okay, let me write the whole form again. It looks like A sine KX. And because they are not particularly care about which direction this wave is traveling, you can pick minus or plus, I don't care. And then omega t. And because they also don't care where this wave is about to start. So let's take to be 0. Doesn't matter, right? It's continuous wave. So in this case, what you can write down is going to be 0.12 meter. That's your amplitude. Sine K, already figured out, pi over 2x. Omega is 10 pi. And you are done.
Okay.
Okay, this is very straightforward that we can just from now on write down the wave function. Any questions so far? Looks pretty good, yeah? Try again. Next. All right, now. The transverse wave on a string is described by the following function. Determine the transverse speed as a relation and everything, all right? All right, we'll do that. And B, what are the wavelength period speed of propagation of this wave? Actually, I should put the B first because B is like reading out what is going on, and then part A, you need to do some derivatives and stuff, all right? But it should be straightforward, guys. Right. You want to attack part B first? I think that's make more sense, right? Logically, let's attack part B. All right, guys, I'll give you some head start. What should be the wavelength, period, and speed of propagation? Write down on your own tablet or whatever paper things that you use to write, and then we'll compare notes at the end. Sounds good? All right, thumbs up. Oh no, that's the wrong one. No. Okay. Wavelength, guys. So all you need to do is just read it out. Just read it. Here we go. Whatever the factor comes in front of X, that is your K. Whatever the factor comes in front of T, that is your omega. So that means you can say right away, K is pi over 8. You guys with me? Very good. So once you know the K, if you want the wavelength, you K is 2 pi over lambda. So that means the lambda is going to be 16 meter. Very nice.
Okay.
Now move on to the period or the frequency or the omega. The omega is going to be 4 pi. Yes? Okay, let me give you a connecting concept over here. The blue is the K and yellow is for the omega. Ooh, cool. And omega is 2 pi f or 2 pi over period. So now, because they want the period, so we pick the period. So the period is going to be 2 pi over omega, and that is 2 pi over 4 pi, and that is 0.5 second. Nice. And last, you want to figure out the speed of propagation. So you want the V. Now you can go back to use equal to V equal to F lambda. Okay, let's revise what we have. Or lambda over T, the period, or omega over K. That's up to you. They're all the same thing. But because what I'm seeing over here is I already had the K and omega waiting for me up there. So I'm just going to set omega there, 0.5, K, 16. Pi over 8 there. I'm sorry, wrong one. My bad. sorry.
Okay.
Omega is 4 pi and K is pi over 8. There you go. And that will give you 32 meter per second. All right. Or if you like, you can do equivalently to say that V equal to lambda over period. And the lambda you got is 16 meter. And the period that you got is 0.5 second. So you also get 32 meter per second. Either way, will do.
Okay.
So part B is fine. It's just like reading what you look at or what you are seeing from the equation. And I can even add on top a little bit that this wave is traveling to your left side because you have a positive sign in between. Does that make sense? Okay, so this is a left traveling wave, negative X direction. There you go. All right, just to emphasize that, okay, we understand the whole wave function here. All right, now let's get back to part A, shall we? So part A, determine the transverse speed and acceleration at that particular time, at that particular position X. So substituting T and X at the end, that's easy. The only thing that you need first is just what is the expression for this velocity in the transverse direction. And we said this one can be found from taking the derivative of the displacement with respect to time. And we do it partially because we don't care about the change in the X. So let's go for it, guys. 0.12, stay there. Okay, let me omit the unit here. I do the derivative of the sine, I get cosine. Okay, I'm just copy everything down here. And then don't forget the chain rule. So the chain rule will ask me to do this. I just have to take the argument there and do the derivative. With me, guys?
Okay.
Okay, very good. And that's it. Your chain rule will give you extra 4 pi. And as expected, actually, because that's your omega. Your omega is supposed to pop out in the front. See that omega right here? Yeah, let me show here. Yeah, omega is supposed to pop out here. And that omega came from this chain rule. Oh, let's wait the screen to update a little bit. There you go, right? So here, you know that every time that you're starting from the y, you take the derivative once, you get the cosine, chain rule will pop this negative omega out to the front right there. Cool. That's just a straightforward first order derivative there. So that's 4 pi 0.12 cosine, and everything just follow. Cool. And as you can see, when I do the partial derivative, that function of x just turned into 0 because derivative of a constant give you 0. Okay, that term will just disappear. Okay, all right. And if you want the acceleration, okay, then no big deal. Just do the derivative one more time. So just continue your calculation. Just take derivative of this. So you get 4 pi still there. That 0.12 is still there. And just take derivative of cosine, you get negative sign. And whatever in the bracket still here. So far, so good. And then you do the chain rule one more time inside that brackets there. And now you know that extra chain rule will give you what? Extra 4 pi. With me, guys? So this means you can just move that 4 pi to the front. And at the end, you will get 4 pi square. So shall I do that? All right, so we're just going to move this 4 pi here and just put square there. And that's it. You are done. Okay, from now on, I mean, from this point on, it's easy now because if the question asking you to figure out, hey, what is the speed? What is the acceleration at this time, at that point? All you need to do is just plug in the x and t accordingly, and you are done with after punching some calculator. Cool. All right. So I hope you learned, I don't know, to learn something today, but that is the sort of like infrastructure of everything that you need to treat wave function, and especially the one that we are focusing on, the sinusoidal wave function. All right. But I hope that from now on, reading out the wave function will be something that can be done very straightforwardly. Cool. All right, guys. So if that is cool, then I think this is the good place to stop for today's lecture. All right. Thank you for sticking around.
Okay.
And I'll see you guys next week. Any questions? Okay. All right. Thank you. Thank you for sticking around. I'll see you guys next week. Okay. And we're going to have exam coming up. Yeah. All right. Bye-bye.
Excuse.
Thank you.
Hello.
Hello ครับ